before we get into periodic trends, which is the whole backside of that cheat sheet, I want to add on one little thing to the last lecture where we were talking about cations, anions, and how to name them. If you remember, we drew this shape, and there was +1, +2, +3, and all that stuff written across the top, and that'll always be true. But this area right here was ignored. It's important that it's ignored because that area doesn't have a set amount of rules for each column. The columns differ from each other. But before we talk about why they differ from each other, I just want to talk about a couple general things that we can say is always true about the groups 3 through 12. Verify that what I just said is true. That lowered area is columns 3 through 12. Here's some stuff that you want to know about them. They are all cations. What's that mean that they're all cations? They're all positive. All right? They all want to lose electrons, which is what creates a cation, is whenever an element decides to lose electrons. But every element in that section is a cation. Now, here's the interesting thing. Instead of representing something like iron with a +2, that's not going to happen. Iron does always have a positive charge. However, we treat these elements very differently. We give them Roman numerals instead of numbers. Now, for those of y'all that are unaware, here's the Roman numerals 1 through 6. You'll want to know those guys. There's the Roman numerals 1 through 6. Don't write them down if you already know them. Usually it's number 4 that messes you up. But instead, if I do have an iron that's got a charge of 2, it's going to look like this. Again, this weird thing I'm showing you is only true for the elements that are in those groups 3 through 12. But when you see that, you should think this. This is telling you that it's an iron with a charge of +2. How do you know it's a plus? Because they all are. In other words, if you're looking for those absolutes, anytime you see a Roman numeral show up anywhere, it's representing a positive number. It has to. Because the Roman numerals only show up in this area, which is much bigger on your periodic table than I've drawn it up here. They only show up for that section, and that entire section is completely positive. So with that in mind, how would I write that in its ion form? What's the symbol for vanadium? What? A V. What is this vanadium's charge? +5. Look at the difference here. All right. +5. Positive because all the Roman numerals are positive. 5 because that's a Roman numeral 5. How would you say him? A vanadium ion. Remember, the rules for naming cations say that you just say the name of the element and then the word ion. So this is a vanadium ion. Only half of you are writing everything that I write, and that'll be the half that remembers this on your final exam. You try one. I want you to write the symbol of that using a real number and charge, and also name him. Write down a symbol with a real charge and value, and then also write his name. What charge did you give silver here? +1. Yeah, should have been +1, not just plus. That's a Roman numeral 1. How would you write him? A silver ion. Any questions as to how I'm doing this? This only applies to groups 3 through 12. Take a look at the back of your cheat sheet. Little bit of history. We've got two scientists that I want you to know about in regards to developing the periodic table to where we are today. The first guy was named Mendeleev, and he was the scientist that way back when they were discovering elements, he said, you know what, there's some shiny ones here, so I'm going to put them together. And there's some not shiny ones here, there's some light ones here, some heavy ones here. And he started trying to organize them just based off physical characteristics. And even when he did that, he noticed that certain trends started to form. Certain trends that I'm going to show you today. Now that was Mendeleev. There was another guy named Moseley, and his name is not written on your cheat sheet. There was another scientist named Moseley that is the guy given credit for taking the largest step towards today's periodic table. Because instead of just organizing them by, oh, well, that's shiny and that's not, atomic numbers, protons, stuff like that came into play for him. And that was our big step towards today's periodic table. Today's lecture is the most concentrated look at the periodic table we'll ever have in regard to its dimensions and why things are where they are. So make sure you've got your PT in front of you. If you're watching this on the video, have a periodic table in front of you. And let's check out his anatomy. First off, the columns. How many columns are there? There's 18. There are 18 columns. Those guys are called groups, or they can be called families. Those terms are synonymous, and that's how you'll hear me refer to them. There are 18 groups on the periodic table. There's also rows. How many rows are there? They're numbered for you. How many rows are there? There's 7. Rows go left and right, horizontally. All right. These guys are called periods. You can use this groups versus periods as kind of a latitude and longitude of any element on the periodic table. For example, what is the group and period of sulfur? Find it. Find sulfur. What is sulfur's group and period? What group? Group 16. Yeah, if you look at sulfur, they're numbered for you. He's in group column number 16. What period is he in? 3. Period 3. So they line up together. These should be really easy test questions because I promise there's a couple of them. So make sure that you know the difference between a group and a period. 18 groups up and down, 7 periods left and right. For the F block at the very bottom of your table, really those are in period 6 and period 7, but in this class, I'm not mean about that. I won't usually ask you about those F elements at the very bottom. If you look near the middle right-hand side of the periodic table, you'll see this. Actually, let me get a table drawn. Near the middle, you'll see this. I called that the zigzag or the staircase. Look on your table and verify that you can find it. Yes? This divides the table in half, asymmetrically, but it divides the table into two sections. For some reason, this next thing I'm about to say is so simple, and it matters so much in our next unit, but some of y'all will never understand it. So look. All of the elements to the left of that zigzag are metal. All of the elements to the right of the zigzag are non-metal. So right now, we can already start answering a bunch of questions about elements that you may not have known. Is beryllium a metal or a non-metal? Beryllium, metal or non-metal? Beryllium's a metal. He's located right over here. To the left of the zigzag, he's a metal. What about chlorine? Is chlorine a metal or a non-metal? Chlorine is a non-metal. He's located right over here in group 17. A non-metal. Easy, right? Now, there's a couple exceptions to make your life hard, but note them so that you don't get confused. Up here is hydrogen. Hydrogen is a non-metal. So if I were to re-speak my absolute, I would say that all the elements to the left of the zigzag are metal, except for hydrogen. But all of the elements to the right of the zigzag are non-metals. There's a third class that I want you to know about, and they're called the metalloids. The metalloids are all of the elements that share a flat surface with the zigzag, except for aluminum. Listen to that again. All of the elements that share a flat surface with this zigzag are referred to as metalloids. And these are elements that have both metal and non-metal characteristics. For those of y'all that are writing what I write, it's going to make your notes much prettier in regards to remembering anyway. But it's these guys that are the metalloids, plus the ones on the other side. Again, if they share a flat surface with the zigzag, they're a metalloid except for aluminum. Aluminum is just a metal. So we've got rules and we've got exceptions, but with monkey grapefruit, you'll be able to learn them very quickly. So let's practice a couple more. What is copper? Metal, non-metal, or metalloid? Copper. All right, copper's a metal. He's to the left of the zigzag, but not on the zigzag. All right. What about selenium? Selenium. Selenium is a nonmetal. Selenium's located kind of right here. He's got a corner touching the zigzag, but that doesn't matter. It's only a metalloid if you have a flat surface touching the zigzag. What about tellurium? What is tellurium? He's a metalloid. There he is, right there. He's got a flat surface with the zigzag. What about hydrogen? Hydrogen is the only nonmetal that is on the left of the zigzag. What about aluminum? Aluminum is metal. He's in a metalloid position, but he's an exception. He's to the left of the zigzag. He's the only element with a flat surface that's not a metalloid. I can ask 10,000 questions on this topic, yes? So make sure you understand this, and if you don't, watch this video again. I'm going to keep redrawing this periodic table. You're welcome to do so in your notes. That is my suggestion. The families have names. Ooh, wait, what's a family again? The groups. Ooh, what's a group? The columns. Don't come back and say families. That's weird. All right. Groups are families and families are groups. Yeah, it's the columns. The ups and downs, they have two names, groups or families. You need to know some of these family names. Group number 1. These guys are called the alkali metals. They are very, very reactive, and I'll explain why in a moment. Right next to them is group number 2. These are the alkaline earth metals. My section in the middle here, 3 through 12, which again is much bigger on your table than I've drawn it up here. These guys are the transition metals. What word do all 3 of these families have in common? Metals, which kind of reiterates another fact that we already learned. Everything to the left of the zigzag is a metal, so this should help with that brain process of remembering that. Because these really are the family names, and they all have the word metal in them. I'm going to skip over to group 17. These guys are the halogens, and again, I'm going to elaborate on these elements in a moment after we get this written. And finally, there's a group, a family that you've already learned because we have used the noble gases. Let's talk a little bit about these guys. First off, you'll notice that your notes say that the alkali metals and the halogens are very, very reactive. I want you to understand why. Look here. The closer an element is to its octet, the more reactive it is. When it's just 1 electron away from being stable, it gets really, really reactive because it can taste stability. Look at the halogens. How many electrons away are they from being stable? 1. They've got 7 dots in their Lewis structure. If they get just 1 more, they've got their 8. But look at my alkali metals. How far away are they from being stable? Also 1. They're just 1 away. They don't want to gain 1. They want to lose 1 instead, but they're just as close. The alkali metals and the halogens are the 2 most reactive families on the periodic table. If you mix them with something, they will almost always react with that thing. What's this made out of? We hope silver, right? Where's silver? What family is silver in? Yeah, my ring is in the transition metals. The transition metals are not very reactive. What happens if I drop this ring in water? It sinks. Nothing happens. Because silver is not very reactive. Listen, look. Here's how it works. The closer you get to the middle of the periodic table, the less and less reactive things become. But the further you get towards the halogens and the alkali metals, the more reactive things become. Except for those noble gases. All right? The noble gases aren't reactive at all. They already have their octet. So listen to what I say one more time. The further you get out on the periodic table, the more reactive the elements get. Out to group 1 and out to group 17. Group 18 is not reactive at all. So they're the least reactive elements. We call that being inert. That vocab word's on your cheat sheet. But the noble gases are inert, non-reactive. They don't do anything. They're boring. But the alkali metals and the halogens, woo, crazy reactive. The other elements will react, but the closer you get into the middle, the less they will. Does that make sense? It's actually kind of good that the transition metals aren't very reactive. It's the reason that you're familiar with many of them. All right? The reason that we can make so many things that we use on a daily basis, like steel and copper and gold and stuff like that, the reason we use those things in everyday life is because you don't have to worry about it reacting so much. The reason we use stainless steel in cooking is because there's a bunch of chemicals that get thrown on that when your food's being made, and it'd be a bummer if chemical reactions were happening every time they chopped up your chicken or whatever. The halogens also have some chemicals you're familiar with. I want to point out that the halogens are excellent killers. They're very, very reactive, and they're excellent at killing things. You can go right down the list of halogens and recognize a bunch of stuff. Where do you see fluorine on a daily basis? In your toothpaste, because the whole point of the fluorine is to kill the nasty stuff that's in your mouth. But it will also happily kill you. You shouldn't be eating your toothpaste. If you go home and you down a bottle of Crest every night, you're in bad shape. What about the next halogen, chlorine? Where do you see him? In pools, right? Because y'all are nasty little monkeys that pee in the pool. Actually, your pee's sterile, so it's not even for your pee. But it's for all the other stuff that might be living and propagating in that water that could cause disease if the chlorine didn't kill it. So the halogens are really good killers. Anyhow, I've covered a lot of stuff about these. Make sure you know where they live. We can try a couple. What family does magnesium belong to? The name of what family does magnesium belong to? The alkaline earth metals, because all the elements in group 2 have that name. What family of elements does bromine belong to? Bromine is a halogen. All right, I'm going to ask very direct questions like that on next week's test. So make sure you know where the stuff is. The last thing we're going to cover is the most helpful part of recognizing all these different parts of the periodic table, but it's the one, this will be the most test questions you miss is over this next topic. So, focus. We can tell a lot about elements by comparing the location of one element to the location of another. But when I say that, I mean is the other element we're comparing to the left or to the right of it? All right, my left and right are swapped from yours. Or are they above or below it? And let me show you what I mean. I'm going to start with something called atomic radius. Now, you can follow along on your cheat sheet in the bottom section called trends, and you can see these vocab words that I'm saying. But the atomic radius looks at the size of an atom. Hey, is an atom big or little? Excuse me? Little, right? You can't see atoms. They're teeny tiny. Now, the size of all atoms are little. But when you compare the atoms of one element to the atoms of another, there is a difference in size between the two. All atoms are little, but comparatively, they come in different sizes. Just by looking at where the elements are on the periodic table, you can tell me which element has bigger atoms and which has smaller. And here's how it works. For atomic radius, the further left you go and down that you go, the atomic radius increases. So understand that these arrows I've drawn are pointing towards where things are getting larger. So right away, you can answer a golden question of chemistry. What element on the periodic table has the largest atoms? Francium. Francium has the largest. Why does francium have the largest? Because he's as far left and down as you can go. Which bears the next obvious question. Which element has the smallest atomic radius? Helium. All right? Understand that if the arrows are pointing towards where stuff is bigger, well, then stuff is smaller the other direction. But more commonly, these questions will come with a list of elements, and I'll say which has the largest atomic radius. So let's practice. Which of the following elements has the largest atomic radius? Zirconium, titanium, or vanadium? Zirconium, titanium, or vanadium? Which one has the largest atomic radius? Don't answer. Give a second. All right, those elements are located right here. What did I say? Zirconium, titanium, vanadium. Which one has the largest atomic radius? Zirconium. Of the three, he's the furthest left and down, right? Which element has the smallest atomic radius? Make sure you always listen to the words. Silicon, phosphorus, or sulfur? Which of these guys has the smallest atomic radius? Sulfur has atoms that are the tiniest because he's further to the right than the others. Silicon is further left where it's larger. Do you see how I'm doing this? There are two other trends that you need to know, and they go the opposite of that one. Both of these other ones increase right and up. So, what you need to remember is that only the size of the atoms gets larger towards francium. These other two get larger towards fluorine, we're going to say. If you look at your cheat sheet, you'll see what they're called: ionization energy and electronegativity. You've got some definitions there. The ionization energy is the amount of energy it takes to remove an electron from the atom. If you look at fluorine sitting up there, he doesn't want you to remove an electron because he wants to gain an electron. Because of that, the amount of energy it would take to remove an electron from fluorine is very, very high, which is why ionization energy increases right and up, the opposite of the other trend. This is also true for electronegativity, which is an atom's attraction for electrons. Fluorine has a high attraction for electrons. He really wants to gain just one. So it increases the same direction. So let's practice. This should just make your brain work the opposite way. Which of the following elements has the lowest ionization energy? Hold on. Lithium, sodium, or potassium? Don't answer out loud. Listen to my question again. I want to know which one has the lowest ionization energy. What's the answer? Potassium has the lowest. All right? We know that ionization energy gets higher as you go up. So this is the one that has the highest. I wanted the lowest. It'll be the other direction. It's fun, right? Which of the following elements has the highest electronegativity? Iron, cobalt, or nickel? Listen to my question again. Which of those three elements has the highest electronegativity? What's the answer? The answer is nickel. Electronegativity increases towards the right, which will make nickel the right one. You'll notice at the very bottom of your cheat sheet, there's a diagram that does arrows, the same way that I do here. If you don't like the definition, you can look at that chart. But I do promise you that come test time, you won't have any of that stuff in front of you. You'll need to know it. So it will take some practice. Questions over periodic trends?